So what we're going to do today is we're going to talk about reaction mechanisms. And here's the idea that typically reactions, they actually take place in a series of steps. We only typically look at the overall equation, but more often than not, a reaction will take place going from one reactant to an intermediate product, and then from an intermediate product to a final product. So let's take a look here, and I wanted to define for you a couple of things here. And the first thing I want to define for you here is an elementary step or an elementary reaction. So whenever we have multiple steps taking us from original reactants to our final products, each individual step we call an elementary step or an elementary reaction. And there's different names for these, and it depends on how many particles actually collide. So whenever we have an elementary step, the reaction is caused directly by collisions of the molecules of the ions and the reactants. So we can actually write rate laws directly from elementary step equations, which is something we cannot do normally with any kinetics problem. Now I want to point out a few things here. If we just have one thing that's banging into by itself and it's reacting and separating out, we call that unimolecular. If we have two things that are hitting into each other, we call that bimolecular, and that can go one of two ways. You can have two of the same thing hit into each other, or you can have two different things hit into each other. Unimolecular and bimolecular are pretty common. When you start getting into termolecular, that means you have to have three things that have to hit into each other. And that could either be like two of one thing and one of something else, or three different things. That's really, really hard if you think about our collision model, and the collision model being simply, hey, we have to have these things hit into each other, and if we have to have three things hitting into each other perfectly, all aligned and with the perfect amount of energy, chances of that happening are very, very low. That was supposed to be an unhappy face, but it made it into a little line there. Now, Zumdahl defines a reaction mechanism as a series of elemental steps. So anytime you have more than one step in a reaction, but there must be these two requirements that are met. If you add up the elementary steps, they must overall give you the balanced equation for the reaction. So it's kind of like Hess's law in that regard. And then two, the mechanism must agree with the experimentally determined rate law. And that's a little more clunky, and we'll get to that in a little bit. Before I go any farther here, whenever you have a series of steps, there's always going to be a slow step. So one of the examples is like having a funnel. The worst funnel in history, right? So if we put stuff into here, it doesn't matter how wide the mouth of this is, we're only going to go as fast as the opening down below here. A better example would be like you have a Ferrari, because who doesn't, right? And you're on a road and you are driving there, and we're looking from overhead, and in one lane you have a semi-truck, and the other lane you have a semi-truck, and you are in the Ferrari right behind here, again in a boxy Ferrari. Guess what? Just because you want to go fast, you are only going to go as fast as the slowest vehicle. So if these guys are both going in a race of this guy's going 55 and this guy's going 55.1, and you could go, I don't know, 250 miles per hour, you are still going to go at the 55 mile per hour thing. That's probably not the greatest example, but hopefully you understand that whenever we have a reaction or multi-step reaction, you only go as fast as your slowest step. So we're going to take a look at this example here, and this is our overall net reaction. Now remember, in order to have a reaction mechanism, you have to have one of two things. You have to have two things to work. One is when you add up your individual reactions, they have to equal your overall reaction. Now I don't want to do any crossing out here because I want to show you how this works, but if you were to add these two up and cancel out things that are the same on opposite sides, you'd end up with this equation. So if we go back up here, number one, some of the elementary steps must give you the balanced equation. That's a check. The second is the mechanism must agree with the experimentally determined rate law. Now here's where I want to point out something to you here. The slow step always determines your rate law. So if we know if we can write the rate law for the slow step, we're going to know the rate law for the overall reaction. Now what's cool, these are elementary steps. Both of these are elementary steps. So with elementary steps, we can actually write the rate law by their coefficients. So the rate for this first one, we'll call this number 1 and number 2, right? So rate 1, if we did this, that's going to be equal to K, we'll call it K1 because it's for this reaction. And we have two NO2s, correct? So that's the same thing as NO2 squared. So it's the same thing as saying, if we looked at this, they're writing it as NO2 plus NO2, but couldn't we write it just like this, 2NO2? And the coefficient being 2, that would be our exponent. So that would be the rate law for the slow step. We can also do the rate law for the fast step. And the rate law for the fast step, we'll call it rate 2, is going to be equal to K2. And in this case, you see we have CO with a coefficient of 1 and NO3 with a coefficient of 1. And so we're going to write CO, that's, I'll put a C in front of that, CO times NO3. Both of these are raised to the 1, but if they're raised to the 1, we never bother actually putting it in here. Now, here's the thing. For right now, in this particular example, this right here, this is our slow step rate law. And if you take a look at our overall reaction, do you see how there is NO2 in the overall reaction? And what that means is that this rate law that we just did for our slow step, that is the rate law for the overall reaction. So the overall reactions rate law is going to be this. Rate is equal to K times NO2 squared. Now you may be thinking, well, what about the CO? Well, clearly the CO has an order of 0 because it does not impact our rate in any way. So what's really kind of cool about this is that if you have elementary steps, you can actually write the rate law from the slow step, and you can write it from the molecularity. Molecularity means how many things are banging into each other and the coefficients. And to remind you here, the different molecularities, in this case right here, we'd be having 2 of the same thing. This would be a bimolecular elementary step. Yeah? Now, whenever we have, and by the way, I wrote it again here in a much neater fashion, and I'd encourage you to read through my notes here. I decided to do something different today. I decided that I was going to keep my notes as normal and just write on the sides of them so you guys can see the original notes throughout. Now, if we have a really complex reaction, we can actually come up with the rate law or the rate expression. So this rate expression and rate law, they're kind of used interchangeably, can be determined by looking at the individual steps. So what we typically do is we write down the individual steps. We have step 1, step 2, step 3, and whatever step is the slow step, right? Let's say this middle one's a slow step, we can write the rate law from the molecularity. In other words, by using the coefficients. So writing using molecularity is just a fancy way of saying use coefficients, right? So we can then write the reaction rate expression in terms of the slow step. So whatever our slow step is, that's going to be the rate law for the entire equation. But there's a problem. What happens if the slow step has an intermediate that isn't included in the overall reaction? Now we're going to do this together here. So we have 2 equations here, right? We're going to call this equation 1 and we're going to call this equation 2, right? If we were to write the rate law for this, we would go to the slow step, wouldn't we? And we'd go, all right, rate is equal to, and I'm gonna say rate 2 here because I want to keep in correspondence with the actual numbers I'm putting here. Rate 2 would be equal to K2 times Knockle 2 raised to the 1 because of the coefficient of 1 in front of this, times No and O raised to the 1. So this would be our overall expression. And you might think to yourself, that's awesome. This is the slow step. This is what the overall rate law is going to be for the equation. But here's the problem. When we look down here at our actual equation, this is our actual balanced equation for this reaction. And we got that by adding these 2 equations together. And you could verify that by canceling out units. Do you see how there is no Knockle in that? Knockle 2, I want to make sure I'm using the right expressions here. This right here is not found in our overall expression. And that's problematic for us because we cannot define a rate law. Like if I gave you this expression right here and then I gave you this rate law, someone who's looking at it would go, wait a second, where's the Knockle 2 and how much of it do we have and whatnot? So our job then is simply this. We must get rid of this. And here's what's kind of cool. And you can't use the word substitution, but essentially that's what we're going to do. So This first equation, whenever you have a slow step that has an intermediate, we call this a reaction intermediate, and these intermediates typically don't exist for very long and they could not be used as our overall equation. What we can do is we can go back to our original equation, and do you see how there's a Nockel 2 here? What we can do is we can use this as an equilibrium and substitute out Nockel 2 in the rate law. And what do I mean? Well, if this first step is an equilibrium, right, doesn't an equilibrium always mean that the forward rate, the rate forward, is always equal to the rate reverse? Isn't that just true? That's what an equilibrium is. The forward rate is equal to the reverse rate. So if I were to write the K expression going this direction and the K expression going, I'm sorry, not the K expression, the rate law going in this direction and the rate law going back the other direction, they'd have to be equal to each other. So if I did that, and I'm going to use just the expression that's done really neatly right here, but I'm going to do it underneath here. I'm going to write KF times NO times CL2. Now, if you're thinking, well, where the heck did he get that? Well, see, we have NO with an exponent with a coefficient of 1, and here we have CL2 with a coefficient of 1, and we don't care about the products when we're going in this direction. So the forward rate is going to look like that. The reverse rate, all we have over here is Nockel 2, right? So we're just going to go, again, we're going to call it K reverse. It does not matter what we call our K's here. K reverse, and it's going to be just Nockel 2. Now, why is that a big deal? Well, couldn't we rearrange to get Nockel 2 by itself, right? And if we do that, wouldn't we essentially just do this? Couldn't we divide both sides by this KR right here? And the end result would be that we would have KF times NO times CL2 all over KR is equal to Nockel 2. And I just realized why I didn't use this, because this is written incorrectly. The way it's written right now, this should actually be KF and this should be KR on the bottom. So what's cool about this is that when you have that expression, what you can then do is you can take this right here and you can sub it back in to this. So we can take this whole expression, which is this right here, all of this, and we can put it into here. So it's going to replace it. So let's ignore this line here, but this is that, right? So when we do that, if we substitute it back in, let's write our overall rate expression right here, and it's going to give us this. It's going to be rate 2, if we want to say it this way, is going to be equal to K2 times KF times NO times CL2, and all of that is over KR. So in other words, I've just written this whole expression right here. I've just written it right there, and that's going to be times NO. Now I want you to do something, notice something here. We can gather like terms. So if you take a look here, do you see we have, not like terms, but constants. You see how K2, KF, and KR are all constants. So what we can do is we can gather them together and call them an overall constant. And then if we add up everything together here, don't we have two NOs right here? Is that fair? So isn't it NO times NO? So wouldn't that give us NO squared times CL2? And that will now be equal to my actual rate. So rate 2 is the rate law equation, so we can now call it rate, our overall rate of the equation. And if you see how it's written over here, what I did here is I kind of explained it. I said K2, KR, whatever. It's just three constants multiplying, dividing each other. That's what I did with this little circle over here. And you get another constant, K, right? And that means that our final equation is this. So this right here is this right here. And what's cool about this rate law right here is that if you take a look at our actual rate expression up above here, which was, oops, sorry, not that. If we take a look at our actual overall expression right here, doesn't it have NO and CL2? Now, here's what some of you guys might notice here. You're going to notice, oh yeah, there's a 2 in front of the NO and there's a 1 in front of the CL, and lo and behold, look at how that exponent is 2 and this is 1. That is a fluke. Do not look at that and think, oh, we could have just jumped to the overall equation and gotten our answer. Does that kind of make sense? Yeah? Okay, now let's take a look at one more example here. So same sort of deal here. We have the reaction NO, or 2NO plus O2 goes to NO2, and we've been given two possible, two steps in our reaction mechanism. And they've told us that this is the slow step. And why does the slow step matter? The slow step matters because that's going to define our overall rate expression. So could we write, and if we, just to keep in form here, we're going to make this number one, this step number one, and this step number two. For step number one, couldn't we write, okay, for rate number two, wouldn't that be equal to NO3, let's put a K in here, and we'll call it K2 as well. Can we call it NO3, concentration? And again, because these are elementary steps, we can actually use the coefficients in front. So we can go NO3 raised to the 1 times NO. Again, we ignore the product. Now, when we write this, and this is what I've done right here in a much neater way, if we take a look here, this NO3, if you take a look at the overall equation, which I'm going to highlight here in a different color, let's color it with this color right here. This overall equation right here, it does not have NO3 in it. So we cannot leave this, and if it did, then if it had just NO3 and NO in that equation, we could say, hey, this is my overall equation, my overall rate, and we'd be done. But we have to get rid of the NO3. And so whenever we have a slow step that needs to have the intermediate replaced out of it, there's going to be a fast step, and it's going to be an equilibrium fast step. And if you notice here, isn't there an NO3 right here? So we can do the same thing we did in the previous problem. We can say that the forward reaction is going to be equal to the reverse reaction. So let's go down to our and I kind of skipped a step here, but let's go, our rate forward is equal to our rate reverse, right? And again, we're going to put K, the names of our constants don't really matter, but we're going to go KF times NO times O2. That's going to be our forward reaction rate, and I got that again from the 1 in front of the NO and the 1 in front of the O2, and that's going to be equal to the reverse rate. And again, all we have on the reverse side, which makes this kind of easy, is all we have is NO3, and there's only a 1 in front of it. So if we want to isolate this, could you agree with me that all we're really going to have to do to isolate this we're just going to have to get rid of this KR on this side, which means divide it over onto this side. So this right here, if I wanted to make it really simple for myself, I could get rid of this, and would I now have expression for NO3? So then, couldn't I take this entire thing right here and plug it back up in for NO3 up here? So I'm going to take this entire expression, and we're going to bring it down here because a bunch of arrows are not distracting at all, right? And I'm just going to write our rate 2 is going to be equal to K2 times this entire expression is going to go in the place of NO3. So that's going to be KF times NO times O2, and all of that's going to be over KR. That whole expression right here, that's this expression right here that we replaced the NO3 with. And then we still have to multiply it by NO. Now again, we can gather like terms, and we are going to do that. We can gather like terms, and we can say, well, not like terms, I keep on saying like terms, but I mean all these constants right here, they're going to match up and give us an overall K. And then whatever's left over, don't we have an NO and another NO? And so couldn't we go NO squared times O2 would give me my overall rate. And if you notice here, what's cool about that is that it matches up with our overall expression. And yet again, if you see the coefficients here happen to match up over here with our overall expression, but that does not mean that that's what's going to happen. So I'm going to stop right here, and then what we're going to come back to is we're actually going to do problems where we work backwards from the rate law, and we figure out what the actual mechanism is. So hopefully this has been helpful. You might want to go back through this, and I'm going to hopefully give you some notes that do not have all of my scribbling over it. Have a blessed day and stay safe.